Hello everyone, my name is Themistoklis Charalambous. I am a professor at the University of Cyprus and I am the technical coordinator of 6G-LEADER. Anna unfortunately couldn't do it and I stepped in last minute, so I'm using Anna's presentation. So I'll try to do my best to support Anna's presentation. The 6G-LEADER stands for Learning Driven and Evolved Radio for 6G Communication Systems. And it started in January already with a consortium of 18 partners that I will describe later. And as Christina mentioned earlier, the total eligible cost is 8.5 million almost, and the grant amount that we received is almost 8 million euros. The mission is to develop AI and ML driven solutions that give sustainable and energy efficient 6G wireless communication systems. And we do this through a few challenges that we identified and through objectives that we set that give the general vision, basically, to set some new standards in wireless communications with innovative AI, advanced antennas, spectrum efficient technologies that I will describe in a bit when I go through the architecture. So this is quite general, but of course the project is supporting innovation. This will be done through hopefully fruitful collaboration among the partners. And one of the main pillars is to strengthen sustainability and have a global impact in 6G worldwide. And this we anticipate to do through excellent research and development. Our goals, these are quite general, but the objective will be shown shortly through our main objectives and architecture. But in the general sense, as most of the project, we want to, of course, bring forward some revolutionizing results that will accelerate the 6G development and enhance collaboration globally and drives societal impact, having in mind sustainability. And the team is consisting of a combination of both academic partners as well as industrial partners and SMEs. And the interesting thing is that we have a good complementarity and we bring together expertise that is complementary to each other. Some of us have participated in the past in other projects together or collaborated research-wise. So we had our kickoff meeting a few days ago and we had very good chemistry and alignment with the objectives of the project. More specifically, the universities and partners are mentioned here. I will not go through all of them because I will have only 10 minutes as far as I know. But we are bringing diverse expertise and I hope we will show this within the project. The key objectives of the project is to optimize 6G Open RAN with AI and ML, and also to enhance the spectrum and energy efficiency through different solutions that I will mention in a bit, where I will describe the architecture and integrate all these solutions seamlessly using AI and semantics. So in brief, the architecture basically is that 6G-LEADER will adopt an open RAN segregation framework where we divide the GNB into the open central unit, the open distributed unit, and the open radio unit. and develop solutions for run control and optimization, AI and ML-driven and semantics-empowered wireless communication technologies, and then use signal processing algorithms and innovations for fluid antennas and the configurable interfaces. Now, going in more depth to architecture, the architecture we includes closed-loop run control based on radio intelligent controllers, the RICs, and we want to use two run closed control loops, one operating on non-real time which is based on RAPs, and the other one near real time, which is based on XAPs, using AI and ML techniques and semantic awareness in this, which brings basically more energy efficiency and reduction in the EMF exposure through different techniques. And we are mentioning some of them: fluid antennas, RIS, computation over the air, I will say a bit more in a bit, power control, resource allocation of FR1 and FR3, hybrid beamforming, and so on. We want to control and user plane radio resource efficiency, again using AI, ML, and semantics, and also computing resource efficiency using AirComp in enabling wireless for AI. We want to do real-time run control also via distributed apps, supporting a third control loop between the open distributed and open radio units, and this in less than 10 milliseconds. And to be able to run this, the project plans to introduce a conflict manager so that any conflicts between the XAPs and DAPs are handled. Now, in the RF part of the architecture, this is based on concepts of fluid antennas and the configurable intelligent surfaces. And the idea is to integrate these increased degrees of freedom that are not taken into consideration now in the current 5G deployments, and give more agility and responsiveness at the transmitter side, and allowing also adjustments on the fly to signal transmissions, characteristics, and so on. In terms of AirComp wireless for AI, basically this leverages on the well-known superposition property, where we have multiple users transmitting information, and then information is used over the superposition of these signals, and there is a transition now from compute after communicate to compute when communicate, and this saves a lot of from preliminary studies, saves a lot of energy and time. Now, in terms of semantics, semantics are basically used to reduce the communication overhead through some information filtering and compression, and this will be used for integration in the Open RAN, enhancing all the apps. And semantics aware task consists of task descriptor and task requirements. The task and descriptor defines the requested machine learning service, the model to be employed, and the target classes. The task requirements include the latency and accuracy requirements that are set by the task to be considered. Now, when we go to the distributed apps, we want to develop apps that are operating in sub-10 millisecond timescales, so that we can get real-time inference supporting RAN functionalities beyond the current Open RAN architectures. And similar to the other apps, the DApps will adopt a containerized architecture, where the DApps will be effectively managed, and they will simplify the integration with other functionalities. And for this, I go to the next one. We will require a conflict manager, exactly because integrating this might bring conflicting demands. And the benefit of having the conflict manager is to mitigate these conflicts between the XApps and the DApps and so on. All these targets and objectives, we will try to showcase them through 5 proof of concepts. Maybe seeing the previous project, maybe we promised too many, but they are all targeting a set of the objectives we set, a partial set. So each one of these are going to showcase some of the objectives that we have and their performance. Specifically, you can see them, but going through them roughly, we want to assist extended reality with the use of UAVs that operate in real time, and this brings a lot of challenges. We want to enhance the broadband experience by using FR1 and FR3 in ways that have not been used before. As I've said before, in that architecture, in the POC 3, we want to have an AI and ML trainable 6G conflict manager so that we have energy efficiency and critical services. The POC 4 is basically trying to import wireless for AI based on computation over there, empowered by semantically aware apps. And finally, we aim to increase, to enhance the multiple access and reduce AMF using different AI and ML techniques for frequency bands and with the assistance of different antenna configurations through fluid antennas and reconfigurable surfaces. And with this, I conclude my presentation.